Okay, section 3.8, we're going to be going over Taylor polynomials. And Taylor polynomials are used by our calculators, by computers, to be able to calculate those really difficult functions like sine and cosine, and when we want to take the integral of them or the derivative of them, whenever you plug in like sine of 33 degrees, you get an answer on your calculator. But your calculator has to be able to compute that in some way. And the way that it computes it is with a Taylor polynomial. So Taylor polynomial, it's just a polynomial, but the more terms that we have in that polynomial, the closer and closer and closer it will get to being an exact answer. We can get really, really, really close. So let's switch over here to Desmos, and I will show you an illustration of how Taylor polynomials work. Okay, so here we are with a Taylor polynomial expansion, and what this shows us in red is the function the sine of x. Now Taylor polynomials also work with geometric series and series functions, and so to be able to graph this Taylor polynomial, we have to write it in series notation. Now we're not really going to be working with it that way, but that's what's going on right here. This is the series notation of a Taylor polynomial. Okay. Then what a is, in this case, a equals 0. So that means that we only have one term right now that we are looking at. And so this is not a very close approximation. So we are going to move a up and see what happens. As we continue to move a up, we are adding on terms to our polynomial. And I'll show you how we find all of these terms for a polynomial. But I just want you to see how the more terms we add on, the closer we get to a very, very close approximation. Now see, look, this is exact. I mean, this isn't even a close approximation. This is an exact approximation of sine x from 0 to just before 1.5. We're still exact. Right at 1.5, it looks like we're going to be off. Maybe just a tiny, tiny little bit. So let's go up one more. See, now with 3 terms, now we are exact between 0 and, well, at least 2, maybe 2 1/4, and then it starts to get off again just a little bit. So the more we add, the more terms we add, now we have 4 terms. And then look how close our approximation is. Now we're good all the way through pi and negative pi on both sides. Okay. All right, our purple function's starting to look kind of funky, but we are getting closer and closer and closer every time to our real sine function. All right, just keeps going. So this is just another way to be able to identify functions in a way that we can use on our calculator or that the computers can use. This only goes up to 10 terms, but look at how close our approximation is now. It is exact between -8 approximately and +8. So 7.898 to -7.898. We are exact between those two values. Okay, so that gives us a little bit of an idea visually of what Taylor polynomials are. Okay, so back to our definition. Taylor series is a function, and what this function is made of, it is made of, let's start off with, let's say you have some function f at a. The way we're going to find our Taylor polynomial, the first term is going to just be f of a. The next one is going to be f prime of a times x minus a. Next, the third term will be f double prime of a over 2 factorial. Remember, 2 factorial is 2 times 1, times x minus a squared, plus, and then we just keep going on. The next one would be the third derivative of f of a. So f triple prime of a over 3 factorial, which would be 3 times 2 times 1, times x minus a cubed. And you would just keep going on as many terms as you want in your Taylor series. The more terms you have, the closer of approximation it becomes. Now, if we ever have 0, a equals 0, so the series of for f at 0, that's called the Maclaurin series for f. So we'll also talk about Maclaurin series. Maclaurin and Taylor, the same thing. Maclaurin is just when a equals 0. So breaking it down a little bit, we can look at some individual functions here. So for a Taylor polynomial, if we have a function f at a, so that's an important part right there. If we have the function f at a polynomial with just one term, we call that p sub 0 because the degree of the polynomial is 0. So p sub 0 of x is equal to f of a. P sub 1 would be equal to f of a, so notice p sub 0 is included in p sub 1. F of a, and then we add on to that. F of a plus f prime of a, x minus a. And then continuing on till you get down to p sub 3. This is going to be a polynomial of third degree. F of a plus f prime of a, x minus a plus f double prime of a over 2 factorial, x minus a squared, plus f triple prime of a over 3 factorial, x minus a cubed. Okay, and then again, the Maclaurin polynomials for f is when this a value here is going to be 0. Then we would just have f prime of 0, x plus f double prime of 0 over 2 prime of x squared. So when we're doing a Maclaurin series, we will not have two terms. It won't be x minus 1 or anything like that. It'll just be x squared. All right, so we are going to look at how we find a Maclaurin polynomial. So we're going to look at these functions below. So we have f of x is equal to e to the x, and f of x equals sine x, and f of x equals cosine x. We're going to look at each one of those individually. Okay, so the first one we're going to look at is when f of x is equal to e to the x. So for our polynomial, for p sub 0, they want us to find p sub 0, p sub 1, p sub 2, and p sub 3. So p sub 0 is just going to be f of a. P sub 1 is going to be p sub 0, so f of a, plus the first derivative, f prime of a, times, now in this one we're doing the Maclaurin series, so a is going to be 0. So f prime of a, and then x minus a is just going to be x. Okay, then p sub 2 is going to be all of p sub 1 plus, now we're also going to add on the second derivative of a over 2 factorial times x cubed. No, squared. Okay, and then p sub 3 is going to be all of that plus, I'm going to run out of room there, so I'm just going to add the end one on here. So it's going to be all of this, plus the third derivative of f of x over 3 factorial times x cubed. All right, so first one, we're going to find p sub 0. So we want to know f of x. Then we also need to know what f of a is. When we're doing a Maclaurin series, a is equal to 0. So we have f of 0 is equal to e to the 0. And so then our coefficient, c sub 0, our coefficient is going to be 1. And for our polynomial of degree 0, we will have 1. Okay, so now let's go down to our next one. So f prime of x, well, the derivative of e to the x is e to the x. So that's nice. F prime of 0 is going to be e to the 0, which is equal to 1. And so our coefficient is going to be 1. And our polynomial of degree 1 is going to equal 1. So make sure bring that down. 1 plus f prime of a, which f prime of 0 in this case is 1, times x to the first power. So we get the polynomial 1 plus x. Okay, next one. Second derivative of x is equal to e to the x. Plug in a, which in this case is 0. It's 1 again. Our coefficient is 1. And then our polynomial with degree of 2 is going to be what we previously had, which was 1 plus x plus the second derivative of a, so f double prime of a, which is 1 again, so our coefficient is going to be 1. This time we have to do the over 2 factorial. Now you could think of this one as being over 1 factorial, but that's just going to be 1, so that doesn't change anything. And then the first one is also over 0 factorial, which is just 1. So we don't worry about the factorials on the first 2 terms. So 1 over 2 factorial times x squared, which then simplify all that, we get 1 plus x plus 1/2 x squared. And then our last one would be the third derivative of f of x, again, is equal to e to the x. Then plug in a, which in this case is 0. So our coefficient is still going to be 1. And then p sub 3 is equal to everything that we previously had, plus our coefficient, which is 1 over 3 factorial this time, times x cubed. Let's rewrite that. So 1 plus x plus 1/2 x squared plus 1/6 x cubed. And then that would be our final answer. So if we went back onto Desmos and we looked at our original function, f of x equals e to the x, and then we also looked at this polynomial of degree 3, you would see that they would follow each other very closely to a certain point. Okay, so now let's look at the sine of x. Actually, I'm about out of time, so I'm going to end this video. We'll start with sine of x and cosine of x on the next video.